Okay, so let's see that the Fourier transform um, defines a unitary operator in L2. Okay, so with Planck-Harel theorem, we know that the Fourier transform in L2 is an isometry. And if we have a isometry that also is surjective, then this will give us an unitary operator. So let's see that the Fourier transform in L2 is surjective. Okay, so after the Fourier transform is a symmetry, then we know the image of the Fourier transform is a closed subspace of L2, and well, we want to prove that it's surjective, so let's assume that the image of F is a proper subspace. Let's say image of F A, which is not included in L2. Okay, so then there must exist a function g such that the integral Rn of F transform gy must be equal to 0 for any F L2 always in Rn. Okay, so if this is g and we multiply it by a Fourier transform of F, it must give 0, it must be equal to 0 if this g is not in the image of F. Okay, so now we will use a property of Fourier transform that we described before, which will extend f in g to L2, and it's the following: the integral of fy gy transform here, that we already know that it's equal to 0, is equal to the integral Rn of fy g transform. Okay, and we know because of this also has to be equal to 0. Okay, so we use this property that we already uh, used for L1 when we announce all the properties for the Fourier transform in L1. Now we're going, this property extends to L2. And okay, so we had a G that have F in the image and G that is not in the image. And now with this property we have that for all F, then the multiplication with G transform has to be equal to 0. So this is for any F. So as this multiplication, this integral has to be 0 for any F, that tells us that G must be equal to 0. And this contradicts the fact that about what Heidel's theorem told us, and that is that the norms are equal. This should be a term form. The norm 2 are equal. There must be different to 0, so this is a contradiction.